Good morning, ladies and gentlemen, and welcome to our webinar Power Skiving on EMAG VSC 400 PS machines. My name is Martin Abendschein. I'm an application team manager in EMAG Technical Sales Department, and I am responsible also for the VSC 400 PS machine type. And together with me is my colleague Daniel Nille.
Hello, my name is Daniel Nille. I've been working in development at EMAG for a long time. And especially in the last year, I've been increasingly involved in the power skiving process.
Okay, so let's start the webinar. If we have first a look in the history of power skiving, so we have to say power skiving is not really a new technology. It was already developed beginning of 20th century, and it was then an application beside of the normal shaping and hopping applications, but at that time, due to the poor tool quality and also the not very developed machine concepts and especially missing control units, it was not really efficient to use power skiving at that time. So beside of this, it was a little bit on a lower level applications, but nowadays and in the past years, there was a huge increase in development regarding the control systems and control units, especially also in the tooling side. So nowadays we can use power skiving really as a very efficient application beside of the shaping and hopping systems.
Yes, how does power skiving exactly work? We have a coupling between the main spindle and the milling spindle. You can imagine it like a gear where the teeth mesh with each other. And if we have a look at the tool is in the machine on the axis crossing angle, and if you have a look at one teeth, if the teeth goes into the workpiece here and comes out here, it makes a movement in a set direction. And so every teeth cuts a small chip out of the gearing. And if we have a look at this chart here, we need the Z axis for the for the movement of that we can machine the whole length of the workpiece. Then we have a Y axis. The Y axis is for the infeed, and we have the X axis. It's for the positioning of the tool, so that we are in the middle of the center height. We have the B axis. Is possible to with the B axis, it's possible to machine axis crossing angle between 5 and 45 degrees. Normally, it's also possible to machine with other tool axis crossing angles, but it makes no sense normally. We have already made, for example, this gear, gear here. You can see it's a warm gear. It's 47.5 degrees. That's also possible. In this case here, we have an example from machining with power skiving. We have here a video. Here we have machined gear with model 1 and 46 teeth. We have here 2 roughing cuts and 2 finish cuts. The roughing cuts are faster than the finish cut. And we need the finish cut to get the perfect quality on the tooth trays. In this case here, we have machined the part with air. You need something to get the chips out of the process, because if they come back into the process, you get chip clamps, and they are not good for the tool life. So we have also the possibility to use air or cooling lubricant. For this, we have we can easily switch between the both with M function.
Daniel, I think you answered the question already, but we got already the first question. So in the video, you have showed dry processing. Can it also be done wet? What are the advantages?
Yes, it's also possible to do it wet. I'm a fan of dry machining because the chips don't glue on the workpiece, and you don't have to clean the workpiece after the power skiving process. But sometimes if you have maybe a shoulder at the end of the gear where you get a lot of chips, then it's sometimes better you use cooling lubricant, because you have a higher pressure to get the chips out of this area.
Okay, thanks.
Yeah, what is the application for power skiving? We can machine internal and external gears with power skiving. That's everything possible, especially normally we use it for internal gears. Which other possibilities do we have to machine internal gears? We have one possibility is broaching, but broaching maybe is not possible when you have a plane or shoulder at the end of the gearing. Then you get a collision. You also can do no flank modifications with broaching. The other possibility is to use gear shaping, but gear shaping is slower than power skiving because of the return strokes. External gears, normally you can produce all gears, nearly all gears with power skiving, but if sometimes you have external gears with a small distance to a shoulder, there you can use the hobbing process because of the diameter from the hobbing tool, then you get a collision. The distance is for with power skiving is lower. You need a smaller distance to the shoulder, or you can produce a smaller distance to the shoulder than with the hobbing process. And you can also produce external gears with gear shaping, but gear shaping in this case also slower than the power skiving process. Another thing is complete machining. We can machine one part completely in one machine. That means we can do some turning processes, we can do the power skiving process, and we get the perfect quality, especially the concentricity between the references and the gearing is perfect with power skiving because we don't have need two clampings. What are the advantages of power skiving? We have lower cycle times than with shaping, for example. We have the possibility to produce gear modifications. Gear modifications will come more important, especially for electrical cars, for example, because former times you had the engine was very loud, and now you don't have an engine, so you hear more the gearings, or hear more the gears. And because of this, you often use then gear modifications to get the gear the noise of the gear lower. For example, crowning or something like that. Yeah, we can produce a very high gear quality and with low surface roughness.
So if you now come to the process chains, so in the past or mainly used at the moment is a process chain like you can see here in the upper line. So we have two turning operations, op 10, op 20. Then we have a shaping process, we have a deburring process and hardening process. And at the end, if it's necessary, also a grinding process. By the way, all blue colored processes can be done on AMAC machines. So this is a, let's say, traditional way. And if we are now talking about the changes with power skiving, you see it in the lower line. Here, of course, we still have the op 10 for the turning of the first side, but then we can use already our VSC 400 PS machine for the turning operations in the second side. And in addition, also for the power skiving operation. After that, we would have the hardening and then also the grinding process.
Martin, can I please disturb you? We have a question. Sure. What are the advantages of combining turning and power skiving? Why are the processes not performed in separate machines?
Okay, so of course it's possible to do it also in separated machines. But if we have a look on the process chain again, in the beginning I showed we have op 10, op 20, then we have the shaping. And if we are doing the op 20 and the shaping, in this case, power skiving process in one machine, we have only one clamping, which means we have only one setup. So we do not have an error or a fault between op 20 and the shaping process due to clamping reasons. So there is no clamping error inside between. We are doing the turning process of all the references, which means that we are doing turning and power skiving in the same clamping, so the accuracy of the part is much higher. We have lower processes, which means, and this is what I want to show you here on the next slide, which means that we need lower invest costs. So we have a lower capital commitment. We have lower space, which we need because we have two operations or two machines less. And beside of the space, of course, we do also have lower energy consumption costs because we have not so many machines. And last but not least, at the end, we can also shorten the complete production line time, which means the throughput from the war part to the finished part is shorter because we do have not so many processes. Okay, so if you now have a look on the machine itself, you can use the machine in two versions. The first version, which you can see here on the left-hand side, is we have a standalone version. In this case, we have the machine and we have a so-called L-type conveyor band, which goes through the machines. So the operator puts the part manually here, the war part manually here on the L conveyor. Then the part will be transported into the pickup area. At the pickup area, the machine picks the part by itself by use of the clamping jack, transport the part into the working area. We are doing the turning process, we are doing the power skiving process, we are doing the deburring process, and then bring the part back to the finished part pallet and transport the part out. And the operator can here then change the finished part into a new raw part. This is a standalone solution which you can place everywhere in your production beside of the other production lines. If we are talking about a complete automation process inside a production line, of course we have the same machine type, but now we change the L-type conveyor to a so-called shuttle principle. On the shuttle we do have only two pallets, one for the war part, one for the finished part. The principle is the same. You have a robot unit, you have a gantry unit or similar things to place the raw part onto the raw part pallet. Then the part will be transported into the pickup area. Machine takes the part, brings it to the working area, machine the part, brings it out, and the finished part can easily be taken here by a robot or by gantry from the finished part pallet. So we do have both possibilities. We can use the machine as a standalone machine, or we can fully integrate it into a complete production line.
Yeah, what options do we need for power skiving? First, we need a B-axis. We need the B-axis here for set up the axis crossing angle. I already told you we can machine with the axis crossing at between 5 or 45 degrees. You see the B-axis is very stably here mounted into the VSC 400 PS on both sides. You see here the two milling spindles. And here the 6 turning tools back of the milling spindles. What do we also need? We need a milling and a main spindle with a direct drive and a higher resolution incremental encoder to get the perfect synchronization of the axis. Here's some technical data from our power skiving machine. It's possible to produce workpieces with a diameter of 340 millimeters. It depends on the clamping. If you clamp the part in the inner side, you can also machine a part with 400 millimeters. The maximum workpiece height is 160 millimeters, but it also depends on the clamping device. The maximum swing diameter from the chuck is 420 millimeters. And on our B-axis, we have mounted 6 turning tools with a BMT65 interface. And we have a possibility to put 2 milling spindles into the B-axis. It's also possible to use only 1 milling spindle, but if you use 2 milling spindles, we have some options. For example, you can do the rough cutting with 1 milling spindle, and with the other you can do finish cut, or you can use both spindles for to get the double tool life, or to get more time till the worker has to change the tools. Yes, that's yeah. And then we have another possibility that we can make, for example, 2 earrings on 1 workpiece. It's also possible to use 2 tools on 1 milling spindle as a the one tool is up on the upper side of the other one. But in this case, we always have to check because of interreference contours. Our milling spindle has a maximum speed of 7,000 rounds per minute and the main spindle 3,400. We often get the question, what is the maximum speed for the coupling? And we tested it. We know that we can couple both spindles up to the maximum speed. That means 7,000 and 3,400 speed in the coupling is possible.
Okay, Daniel, there's another question coming in. How long is the tool life?
This question is a bit complicated to answer. It depends on the workpiece. Sometimes you have a tool life, if you have a big workpiece, maybe you have a tool life about 50 workpieces. Sometimes we already had a process that was the tool life 500 workpieces. But this really depends on the workpiece and what gearing you have on the workpiece. Okay, what gearings can we produce with our machine? We can produce straight and helical gearings. We can produce splines and running gears. As I already told, maximum diameter is 350 millimeters and outer diameter 400 millimeters. We can produce up to 4 different gearings per workpiece. And now we have already tested machining up to module 4, but I'm sure that we can also machine bigger modules because the machine is very rigid. Then we can produce the references in one clamping with the gearings that makes the perfect quality.
Okay, so coming a little bit more into the details of the machines. So here I want to show you the 4 main components which I want to explain today during the webinar. First of all, we do have our machine base made of mineralite. Then we have our hydrostatic guiding principle with our symmetrical design. And last but not least, we do have our machine cooling with 2 circuits. So if you have a closer look to our machine base, you can see it's a new shape machine base, completely made in mineralite. Why mineralite? Because mineralite has a 6 times better or up to 8 times better damping altitude or damping weight compared to gray cast iron. And especially if we are talking about milling processes like power skiving applications, we need a very high vibration damping weight to minimize the influence to the tool and to the workpiece. With this higher damping weights, we can assure that the tool lifetime is much higher than with other systems like with cast iron, and also that the surface quality of the part at the end is much better. On the second side, we do have also oversized screw spindles and linear guideways, which makes sure that the machine is rigid enough for these bigger applications with, let's say, module 4 or even bigger. And another point is we can do also hard turning processes without any special accessories on the machines. Okay, then the second point, hydrostatic guiding system. So we are using a guide cylinder which runs in an oil film in a hardened liner. Maybe you can remember the very big portal milling machines from the past. All of them have flat guideways with an oil film in between, and the collision, and this was especially for collision reasons, that you have no collision influences on these big guideways. And we are using the same principle here in the system. And also here, again, this is one of the most rigid systems which you can have for such processes. And also here we can assure that we have longer tool lifetimes with that. And the second point, which you can see here, as I explained before, we do have our pickup machine, which means the part hangs on the spindle. And so the part is in a vertical direction. And for this, it's very important, especially if we are doing power skiving of internal gears. So for this, we need to have the possibility that the chips fall down directly out of the workpiece. If we are using a horizontal spindle, principle. In this, we would have the part in a horizontal way. We have to go inside with the tool, and now the chips are always inside the gear, inside the part. And here you have to make sure that all the chips come out. Otherwise, you would have chip clampings, you would have some damages on the contour, and in worst case, even a tool break because of these chips inside. With our principle, vertical principle, the chips can easily fall down. So we can make sure that most of the chips are going out and will not influence the process as well. And this is also a big influence on the workpiece accuracy. If we have hanging spindle, hanging part, and the chips fall out, all the heat falls out because the chips have the heat of the process inside. And we can make sure that the chips, the heat comes out of the process and will also not influence so much the quality and accuracy of the part.
We got another question. The question is, what is cycle time if compared with hobbing and shaping? Yeah, normally hobbing is faster than power skiving. If hobbing is possible, yeah, normally hobbing is faster than power skiving. But shaping is normally always slower than power skiving because of the return strokes.
Yeah, and it depends. For hobbing, for inner gears, you cannot use hobbing. So this is then only for the outer gears. And also, like Daniel already mentioned, it depends on the part type and on the application request, module type, number of teeth, and so on, and length, and so on.
Yeah, at external gears, normally, if it's possible to use hobbing, then hobbing is the cheaper process than power skiving. But yeah, sometimes it's not possible to use hobbing, especially if you have a shoulder at the end of the gearing, then you have to use power skiving.
Okay, so coming to the next slide, here you can see the symmetrical design of the machine base in the cross slide. And this means we have a complete closed power flow, which guarantees extremely precise workpieces because the power flow is always in the center of the machine bed and will be covered from the complete part, from the complete machine base and the cross slide. As well, if we have temperature movements inside the machine due to the change of the temperature outside, this here is always symmetrical. This means the temperature will increase the machine in a symmetrical way and will not influence the part quality so much. And last but not least, we do have our two coolant systems for cooling down the machines. So we have one for the machine main components, which means the turrets, which means the machine base, the main spindles, and another one for the electrical cabinet only. And we do not cool down the machine completely to 20 degrees, for example, or 22 degrees. We only cool down the machine temperature in a difference to the ambient temperature, which means if you have outside 36 degrees, the machine will be cooled down to 32, 34 degrees, for example. And why we are doing this? Because if we bring the war part inside the machine, the war part has normally the temperature of the ambient of the area around the machine. And so you have, let's say, 36 degrees in the war part. You bring it into the machine and the machine is cooled down to 22 degrees. So you have a big gap of temperatures, and this will influence the accuracy of the part during the machining process itself. If we cool down the machine only to 34 degrees or 32 degrees, the gap is not that big. So also the influence of the temperature during the process is not that big, and the accuracy of the part will be higher.
Yeah, we got another question. Do you integrate also regrinding of power skiving cutting tools on the machine itself? No, we don't have integrated the regrinding of the power skiving tools. The problem is that if you regrind it in the machine, you have no coating after regrinding, and then your tool life is very low. Maybe in some cases it makes sense, but normally it's not so good if you regrind the tools.
And it's also a question of the process itself. Normally for regrinding of power tools, you need to use oil for the regrinding process itself. So we are using in the machine either only air or coolant, normally no oil. So you would have to mix up all the coolant systems inside the machine. As well as if you're talking about re-grinding, you need to have the grinding wheels on the machine. You have to have the possibility for the dressing of the grinding wheels in the machine. So this makes the machine very, very complex. And also for the operator, it will be very hard to handle all this together in one machine. Therefore, we strictly difference. We have the machine for doing the power skiving, and on the other hand, you need to have a supplier or by yourself a machine and possibility to re-grind your tools.
I know one application where the tool is re-grinded in the machine, and I know that they have to re-grind it after every 5 work pieces, and this makes the cycle time very, very low then also.
Okay, another questions. Does it works on quality QT material 270 to 300 HP, for example?
Yes. Yes, this works. We've already machined a part with this. Yeah, that's possible.
Okay.
So then you can have the best machine if you're not able to program the power skiving process. It was very important for us that everybody can program the power skiving process. Because of this, we created a special AMAC user interface for power skiving. It should be possible for everybody to program the process. You only need the data from the workpiece, from the tool data sheet, and enter it in our user interface, and the user interface creates the program. It's also is very intelligent, the user interface, and you can't make a lot of failures. For example, here you have to see the page of the tool. You have to enter the tool length and the diameter. Then you have to say, do you use a cylindrical or a conical tool? You know, if we do power skiving with a conical tool, it's easy to, no, not easy, but it's easier to do the programming because the tool is on the middle of the center height. If you have a cylindrical tool, the problem is that a cylindrical tool has no clearance angle. So you have to get a clearance angle, like if you have a turning process, you move the turning tool a bit down from the middle. And so you get a clearance angle. And if you have this, the point of contact is not in the middle of the x-axis, and you have to move all the axes that you have the correct movement, and that teeth fit fit together. And so here you can choose if you have a cylindrical or a conical tool. And on the right side, you have a picture that you always see which value you are actually entering. It's highlighted in red. And you also see the tool changes. If you have a left-handed tool or right-handed tool, you can directly compare it with the picture, with your tool, and you can nearly make no failures by entering the values. Then you also have to enter the module, the number of teeth, and the helix angle of the tool. Then we have here some special things. If you need orientation from the serration to another feature, then you can here say where is the position of the tooth 1. If you have a tool with a helix angle, then after regrinding, your position of the first teeth always changes. And here you can enter this, and if you get your tool from regrinding, you don't have to look, oh, what was it last time? It's directly saved into the file of this tool. Then sometimes you have there are some tools which have a profile failure, and then you can do the correction of the profile failure with a movement of the axis crossing angle and the cover angle. And here you also can put it into the tool, because if you have 10 different tools and you need a different correction for every tool, then you can save it directly to this tool, and next time you don't have to look what was last time the correction. You always have it in one file.
Okay, before we go ahead, we have another question already. What are the restrictions on the inner diameter of the product?
There are two restrictions. One restriction is the speed of the spindles, because if you have a very small tool, you need such high speeds, and then you have a problem with the coupling. You have the encoders have a lot of signals, and if you have too much signals, it's not easy to handle. And yeah, because then one restriction is the speed of the spindles, and the other restriction is the tool. Your tool supplier has to grind a very small tool. That sometimes it's very complicated. We have already machined workpieces with, I think it was nearly 32 millimeters inner diameter. That was possible. And we have already machined a part with, I think, model 0.2 millimeters. But then you don't see the teeth. If you have a look at the tool, you nearly see no teeth. Yeah.
And there's also a question of the ratio between the inner diameter and the length which you have to machine. If you have a very high part which you have to machine completely inside, you could have a collision with the tool with the inner diameter of the part at the end. So you always have to investigate in the working area and in the collision for that.
So then the next page of our user interface here, it's the basic data from the workpiece. Here you can choose if you have an internal or external serration. Then you have to enter the standard values, the model, number of teeth, pressure, angle, and so on. And then we have some special things. Maybe here you can produce a bevel serration. And you can enter the rotation of the serration. That you can also here orientate the serration to another feature. And on here we also have the possibility to use the single flank machining. That means that you have two finish cuts and can produce every flank separately. And then after, for deburring, you can, easy way to deburr the part is to use a turning tool, turn over the shoulder, and after that it can be that the burrs go into the teeth again, and then you need an air cut without the tool doesn't touch the workpiece. And then you go through the tool, and so you can break the chips at the end.
Okay, there's another question, Daniel. For the correct machining, we need to measure the total length of tool, or the measuring method is different. So how do we make sure that the length of the tool is on the right in the right parameter for the cutting point for the at the workpiece?
Yes, of course you have. Of course you have to measure the length of the tool. It's the same as you have a turning process. You need the diameter and the length of the tool.
So normally we are presetting the tool outside of the machine, and then we get a measure at the length. We know all the other diameters and parameters out of the tooling data sheet, which we get from the tooling supplier, and then we can put everything together.
Yes, but yeah, I sometimes when I made some tests, I haven't measured the tool. I took the values from the data sheets and set it, entered it in the surface. It makes not so much failures then in the profile. But if your tool length is not it's not correct if you have 5 millimeters difference from the entered value to the real tool length, then maybe you get a failure in the profile. But if it's 0.2 millimeters, so normally it makes no difference. Yeah, then we have also a possibility to do we have some options. Here you can see maybe we can produce crowning or end reliefs. Yeah. They become more important for the gears which are in electrical cars. Then here you can choose which corrections you want to see later in the EMAG feature core. We use this way that you have all the corrections on one page. Here you choose the corrections and later they are shown in the feature core, and you have there all the corrections on one page. You have the corrections of the turning tools, of all the turning tools and of the power skiving tools, and can do the corrections live during the machining, and don't have to go back to the user interface and change there something. Then this is the heart of our user interface. This is the page for the technology. You can here you can enter every value individual per cut. For example, the tool speed, the feed rate, the cut depth, the axis intersection angle, and for example, you can use a intersection angle for every cut a different angle. Normally, you have the problem that if you have a different angle, your position from the middle of the tool changes, but we calculate everything in the background so that you always have the perfect position and your teeth fit together. Then you can enter the cover angle, and if you switch your cover angle during the cuts, you have the problem that you have to do a lot of movement with the axis. You have to move the x-axis, the y and the z-axis, and you also have to rotate the main spindle and the milling spindle that you perfectly fit in the middle of the teeth, and that you have the perfect point of machining. Then you can enter the moving in travel, the overshoot travel, and the axis rotation, as the rotation of the z-axis. With the rotation of the z-axis, you can do a lot of things. For example, when you have a power skiving tool, one flank of the power skiving tool normally cuts better than the other one. And here you have the possibility to say, to do an orientation of the z-axis, that you always only cut on the better flank of the tool. That's one possibility. Another possibility here is for if you have a single flank machining with two finish cuts, then you can set in here, enter here the rotation that you cut the left flank with the first cut and the right flank with the second cut. Then sometimes we have the problem that if you have maybe a shoulder or your workpiece is closed after the gearing, then sometimes you have a lot of chips there. And we can say here that we reduce the speed for a time that the chips can fall down. Yeah, now we have some examples of the gear quality that we have achieved with power skiving. Here the machining was a gearbox with model 0.6 millimeters. Here you see the profile. The deviation of the profile was in this case between 1 and 3 microns. It's quality 4. This is the tooth trace. You can see also quality was between 1 and 3 microns, which is quality 3. And the pitch deviation, pitch deviation quality, also quality 4. Yeah, but here, it's not always possible. It depends on the workpiece. Sometimes you have a number of teeth from the workpiece where it's not so easy to find the perfect tool. Then maybe the quality is not as good as shown. But our machine, if the tool is good and you have a good number of teeth at the workpiece, then you can get this quality which we have shown you.
Okay, so now we are coming to the end of our webinar, and we are really looking forward to your questions now. Please feel free to send them us. Oh, okay. The first one comes in. Do you have experience in hard fine machining with power skiving?
Yes, we have already tested it, but the problem here is the tool life. We had no tool till now which has an acceptable tool life. Our machine brings all the possibilities that it's possible to do hard, fine machining. We have a probe where, with this probe we can detect the gear that we fit the tool into the gaps, and yeah, our machine is very stable that we can do hard, fine machining. But I think the problem at the moment is the tool life.
Okay, next question. How do you deburr the gear runout on the Power Skiving machine?
Yes, as I already told, the easiest way is to deburr it with a turning tool. You turn over the shoulder, and after that you use an air cut with the Power Skiving tool to break the chips completely. That's one possibility. Also, maybe we can do brushing in the machine. It's also possible.
Yeah, so we do have up to 2 milling spindles inside the machine, so we can use 1 milling spindle for the Power Skiving process itself, and the second, for example, we could use for brushing as well, or as a spare part for the process, or rough cutting and finish cutting in the same, also possible. Okay. Is it possible to make swivel bevel plate gears?
Yes, it's possible, but we have to have a look at it, because we have to look if our set movement is enough that we come with the tool to these gears. But our interfaces has the possibility, and it should be possible, but it depends on the workpiece.
Yeah. Okay. Can hardened gears also be machined with Power Skiving? What is the impact on tooling costs?
Yeah, I think it's the same question. Yes, they can be machined with Power Skiving. It's possible, but sometimes the tool life is not very good. We had one test. There was a tool life 5 workpieces. I got no good tool till now to do the hard Power Skiving.
Maybe it's pretty much for shop floor, for workshops, for smaller provider of smaller lot sizes, which have to make maybe 1, 2, 3, or 4 gears only, which they have to harden, and they don't want to grind it afterwards. So then it could be a possibility, but tool life is really the biggest issue at the moment. Okay, another one. Is temperature compensation required during the process?
Normally, no. Normally, we don't need a temperature compensation. If we use air for the removal of the chips, then we definitely need no temperature compensation, because the air has always the same temperature, and the machine is very, the temperature doesn't change a lot from the machine. When we use cooling lubricant, then sometimes it's good to use temperature compensation, but it depends how stable is the temperature of the cooling lubricant. But we have the possibility to do this.
Okay, another one. How serious stable is the Power Skiving process? Do you offer measurement data, feedback, and automatic process compensation? Okay, so for the process, I think it's very, very stable if all the parameters are correct. So if you have the right tooling, if you have the right parameters, the machine itself is very rigid and temperature stable. So from the machine side, there is no problem for that. Regarding the measuring, as Daniel mentioned already, we have a probe inside the machine, so we can at least measure the dimensions over walls. And it depends always on the accuracy which you want to have on the machine or on the part later on. If the accuracy allows it that we measure it directly in the machine. We can compensate already these parameters then in the tool management. But of course, it's not a measuring machine. It's a power skiving machine. So you have to, at the end, you have to measure all the parts again on your measuring machine. And we also do have the possibility after the power skiving machine to put an, let's say, measuring machine in the line. And then we have the possibility to couple both machines together so that we have the feedback from the measuring machine, which we can use then for the compensation in the database of the VSC 400 PS power skiving machine as well.
Okay.
One more. Is possible to make a finish cut by other skiving tool? Yes, this is what I explained before. We have the possibility to have up to two milling spindles in the working area. So you can use one milling spindle for the wharf cut and one milling spindle for the finish cut, of course. Okay, so thank you very much for your participation on our webinar. And if you have more questions, if you have later on maybe some specific questions which you want to send us, please use our email address communications@emag.com. Again, thank you for attending this webinar and bye-bye.